Hello everyone, our project is Online Health Enquiry Chatbot. Our online healthy care chatbot provides medical advice for patients who currently cannot access medical resources. We aim to build a peaceful world and to preserve the thriving of human beings. Our chatbot can be significant in the circumstances of deadly pandemic or non-urgent consultation. Also, our chatbot can also relieve the pressure of medical personnel. This is the workflow of our project. We have three main parts: the triangle agent, the vector database, the seek-to-seek agent. All right, next I'm gonna talk about the question routing model. This part covers the main flow of the question routing model. Basically, it's split into two main parts. First, we do some pre-processing on the data. That means cleaning up any extra information users might type that's not really related to the question itself. Second, we built a text classification model. We fine-tune a big language model to help figure out what kind of questions the user is asking. That way, it's easier to send the question to the right database afterward. Next, let's take a look at the training data we use in the model. We use the healthcare consult dataset as our base, and on the top of that, we did some pre-processing. As you can see, the data is pretty uneven. Some categories have way more than interest than others. Also, 19 samples isn't a lot when we are training a model, so the dataset is both small and imbalanced, which can make training a bit challenging. To deal with the small and imbalanced dataset, we first did the dataset augmentation. We use text replacement to make the model more stable when facing different wording and language conversation to enrich the variety of expressions without changing the meaning. We also use large language models to generate artificial data, creating more consultation examples, especially for underrepresented categories. Here are the two main pre-trained models we select. Let me briefly introduce them. We use a robot with good at understanding meanings and handling complicated language. And we also use DistillBot, which is smaller and faster, great when you need quick results to have limited resources. For training, we use DistillBot based on Uncast and Robot A base and fine-tuned it for our healthcare consultation classification task. We froze the DistillBot backbone and only trained the classification head to speed up training and reduce overfitting. We also experiment with different learning rates. Finally, we use meaning-based training and with ADMW as the optimizer to ensure efficient and stable updates. With the small learning rate, the training loss decreased steadily, and both training and test accuracy rose constantly to over 19%, with minimal gap and indicating stable training and good generalization. With a larger learning rate, and loss dropped faster but unstable, and the training accuracy steadily exceeded text accuracy, suggesting mild overfitting. When training a robot data, a small learning rate led to steady loss reduction and smooth accuracy improvement, ranging around 19% with a good generalization. In contrast, a larger learning rate caused unstable loss and oscillating accuracy, indicating less stable training. Overall, smaller provides a more stable and reliable training process. Now let's quickly compare DistillBot and Robot A. DistillBot showed much smoother and more stable coverage, especially with a learning rate of 0.0005, while Robot A struggled with frequency oscillations. In terms of accuracy, DistillBot steadily climbed past 19% without overfitting, whereas Robot A's performance was much more unstable. For overall, considering stability, generalization, and training efficiency, we found DistillBot to be better choice, and that's why we select it as our final model for further development.
Okay, this part is about the vector database. Let's start with data source and pre-processing. We collected 5 QA datasets across healthcare domains: insurance, medical knowledge, symptoms, drugs, and vaccines. Each dataset was loaded from structured JSON files. We performed data cleaning by removing empty or irrelevant entries, filtering out extremely short questions, and normalizing the text through lowercasing and cleaning special characters. This provided a clean and standardized input for the next stage. Moving on to text coding into vectors. Each question was transformed into a dense semantic vector using a pre-trained transformer model. These embeddings captured deeper semantic relationships beyond surface-level keywords, we typically use 384-dimensional embeddings, balancing expressiveness and efficiency. Next, all questions vectors were aggregated into a matrix and the face index was constructed. We use index flat L tool for precise search and experimented with HNSW for faster approximate retrieval. Both the index and metadata mapping were stored for efficient lookup during inference. Finally, about the retrieval workflow, when a user submits a query, it is first encoded into a vector. So this vector is searched against the face index to find the nearest neighbors. The symptoms retrieves the top k most similar questions and returns the corresponding answer. This pipeline ensures rapid, scalable, and semantically meaningful retrieval, with response times typically under 1 second.
Okay, now I'm going to talk about the sequence-to-sequence agent. If some answers from the chatbot do not satisfy our users, then the sequence-to-sequence agent will provide possible follow-up questions and also the medical advice, recommended examination, general health tip, and psychological counseling. So we first take a straightforward approach, but due to the datasets and training method, we do not have reasonable answers. But we also take an alternative approach. That is, we employ a pre-trained agent with supplement related dialogues from the dataset as context, and let the agent give appropriate answers. So we categorize and collect data entries and remove unrelated information and vectorize text into the database. We use Olama Online API for the inference. We use the LangChain for RG and also prompt engineering. This is the workflow for this sequence-to-sequence agent. So this is an example question, and as you can see, the answer from this agent provides suggestions, diagnosis, and detailed guidance for patients. Currently, because of limitations of datasets and training methods, the chatbot cannot open to the public. In the future, if large databases of medical institutes are supported, our chatbot then can be promoted to hospitals. Okay, next, let's see a demo.
All right, next, I will introduce the key functions of our healthy chatbot. When a user first starts, the chatbot initiates a friendly and personalized greeting, then moves directly into Q&A session. When user asks a healthy-related question, the chatbot processes the input using narrow language understanding, identifying the keywords, extracting intent, and classifying the question whenever it's about symptoms, medication, and so on. It then searches the knowledge base of highly relevant and trusted medical information and generate a clear, professional, and easy to understand answer. After responding, the system checks if the user is satisfied. If the user says no, the chatbot refines the question based on feedback, digs deeper into the knowledge base, and provides a more detailed and personalized answer. And then user can begin the next consultation. This process ensures our chatbot offers fast, flexible, and high-quality support of a wide range of healthy consultation. Thank you. Okay, that's all.